Next, we're going to talk about Euclidean geometry and axioms, postulates, and theorems. So the fundamentals of geometry were established by Euclid, a Greek mathematician who lived around 300 BC. He established the ideas and rules which we now use in elementary and high school geometry. And he had three different rules, I guess. We have first an axiom, which he considered to be a self-evident or universally recognized truth. Next, he had postulates. A postulate is an assertion of truth, to assume a premise, or to take for granted. So these do not need to be proved. But then a theorem is an idea that has been demonstrated as true or proven. So the axioms and postulates of Euclid are given here in their original version from the Elements of Euclid, okay? So here's his axiom. Things which are equal to the same things are also equal to another. So if A equals B and B equals C, then A equals C. If equals be added to equals, the wholes are equal. So these are a little difficult to understand, but this is like the addition property of equality. If equals are subtracted from equals, the remainders are equals. Again, subtraction property of equality. Things which coincide with one another are equal to one another. So if they're the two lines lie on top of each other, then they're the same, and the whole is greater than the part. And then he went on to form other postulates. To draw a straight line from any point to point, so 2 points create a line. To produce a finite straight line continuously in a straight line. Some of these start to becoming a little bit difficult to understand just because of the way he was wording this. To describe a circle with any center and a distance, all right angles are equal to each other, they're all 90 degrees. And that if a straight line falling on two straight lines makes an interior on the same side less than the two right angles, the straight lines, if produced indefinitely, will meet on the side in which the angles are less than two right angles. Again, lots of kind of complex wording for a simple principle. So Euclid said that these postulates are assumed to be true and did not actually attempt to prove any of them. But he did use these axioms and postulates to prove propositions or theorems. And once a theorem has been proved using these 10 assumptions, then it can be used to prove any other successive theorem. And so that's kind of how he built the idea of geometry, using these axioms and postulates. Now, many of the high school and elementary geometry books will actually use the words axioms and postulates interchangeably. Which there is a slight difference, but again, if the books that you're going to be using, you're going to be teaching out of, are going to be interchanging them, you should know that there is technically a difference, but for ease of instruction, we're going to just assume that these postulates or axioms are statements that we accept to be true, and we're not going to try to prove them. Okay, that's what most of the textbooks usually use that. Now, these are some postulates that, in more elementary terms, that I have found in geometry textbooks from high school geometry. So I just wanted to show you them in a little bit more concise way, because some of the axioms and postulates from Euclid are a little convoluted just because of the wording. So here's the first one. Through any 2 points, there is exactly one line. Another way we can say that is 2 points define a line. You'll hear that one quite a bit. 2 points define a line in geometry quite a bit. So let's say we have a point A and a point B. You have 2 points, then there's exactly only one line that is going to go through both of those points, and that line is unique. Next, if two distinct lines intersect, then they intersect in exactly one point. So let's say you have line L here and line M, and they intersect, then there is exactly one point, and that point is unique in which they intersect at A. Next, if 2 points lie in a plane, then the line containing those points lies in the plane. So we have a plane here. We have point A in the plane and point B in the plane. If those 2 points lie in the plane, then the entirety of the line that contains those points will also be in the plane. So if A and B are in the plane, then line, we'll label this line L, is also, the entire line L is also in the plane. Next, if 2 planes intersect, then they intersect in exactly one line. So it's very similar to the third one, except we're talking about planes, intersecting planes instead of a line. So let's say we have a plane. This is a little difficult to draw, but we're going to do our best here. We have a plane here. We'll call that plane P. Okay, and then if you kind of think of it like a ping pong table net or something like that. So you're drawing that up there. Okay, and we'll call that plane O. Okay. Then if plane P intersects plane O, then the intersection is a line, and that line is unique. So that line L, where P and O intersect, is a unique line. Next, through any 3 non-collinear points, there is exactly one plane. Or 3 points define a plane. Again, that's one of those phrases you hear quite a bit in geometry. 2 points define a line, 3 points define a plane. So if you have 3 points, any 3 points, you can draw a plane with them in it. Okay? So this one I like to talk about in the classroom. If there is a point in the corner on the ceiling, and then there's another point opposite it on the corner in the floor, and then your nose, the tip of the point on your nose. There is a plane that cuts through your room at an angle that contains those 3 points. It doesn't matter any 3 points, there is some sort of plane that connects those 3. And that's sometimes hard for students, so I'll say, okay, you know, the point between Latoya's finger, Leticia's nose, and my shoe. The point between those 3 points, there is a plane, because any 3 points define a plane. So it's kind of fun to use your students to try to describe a plane there. Number 6, a line and a point not on that line also determine a plane. So we have a line, and then we have a point somewhere off the line, so we have line L, point A. Well, technically, a line L has 2 points on it at least, right? And so therefore, the 2 points from the line and the opposite point are 3 non-collinear points, and 3 non-collinear points, okay, 3 non-collinear points define a plane. So it's basically the same thing as 5. Number 7, 2 parallel lines determine a plane. Okay, so we have a line here and a line here. So why is this true? Well, there's 2 points on one of the lines, and there is at least 1 point on the other line, and those 3 are non-collinear because parallel lines aren't on the same line, so they have to have at least some points that are non-collinear. So there's 3 non-collinear points. So essentially 7 is the same thing as 5, just in a little bit of different manner. And then the last one, number 8, 2 intersecting lines determine a plane. Okay, so we have an intersecting line here and an intersecting line here. So we got 1 point as the intersection. You have a point on line L. We have a different point on line M. So you can see that those 3 points are 3 non-collinear points, and so they must determine a plane. So basically 6, 7, and 8 are all versions of 5. 3 points, 3 non-collinear points define a plane, and these are just 3 different ways that you could also get 3 non-collinear points. Lastly, and this is an important one, you have to be careful when you're looking at an marked or unmarked figure in geometry. There are some things you're allowed to assume, and there's some things that you're not allowed to assume. So I just wanted to go through some of these examples here. Can you assume that this is a line? Well, yes, it is a line segment with arrows in the end, so yes, that is a line. Okay, you can assume that. The next one, can you assume that this is a right angle? Well, it looks like a right angle, and it's an angle. It's a ray, 2 rays with a common endpoint. But because it's not marked, this does not have a square in the corner, so therefore it could be a right angle. It could be not, but you can't assume that. So we're going to say no. You can't assume that this is a right angle. Now the third picture, can you assume that this is a right angle? Yes, because it's marked as such. Okay. So because that's marked, that is a right angle, we can say that yes, we can assume that's a right angle. Next, can you assume that these 2 angles are supplementary, meaning they add to 180? So this part right here, and then we have the other one over here. Can we assume that they add to 180? Well, yes, because it's a straight line, and a straight line has 180 degrees, we can say yes, that we can assume that. Next, can we assume that these angles have a common side? Well, we have an angle here, and then we have another angle here, and so we can agree that they do have a common side because there's one in the middle. Okay. Can you assume that these 2 lines intersect to form angles? Sure. You have a line here and a line here. We have 2 lines intersecting. You can see the angles, so yes, we can assume that those intersect because that's what the line says. Can we assume that these are complementary, meaning they add to 90? Well, it kind of looks like they add to 90. That angle plus that angle kind of looks like they're 90, but it's not marked as such. So this is no, you can't assume that. Next one, can you assume that these are complementary? Well, yes, you can, because the first angle and the second angle have a marked right angle in there. You can assume that they're going to add to 90 degrees, or yes, that they're complementary. These 2 line segments look pretty much the same length. Can we assume that they have the same length? Nope. You cannot, okay? You cannot assume anything has the same length unless they're marked as such. The last example has these little hash marks in them. Because they have those little hash marks, you can assume that they are the same length. So you just need to be a little bit careful. Just because you can see something in the picture that looks equal, or that looks right, or that looks like it's about 180 degrees, it depends on what kind of markings are on the figures, whether you can assume certain aspects of this figure.